Light emitting diodes, LEDs in short, are semiconductor two-terminal devices. They are associated with one PN junction. Their specialty is emission of light. They require reverse biasing for their operation. The phenomena of recombination is the main reason and the only reason for the emission of light. Recombination refers to a free electron encountering a hole, resulting in joining of the two particles and their disappearance, leaving behind certain amount of energy. In terms of energy band theory, recombination can be understood as a conduction band electron falling into a valence band. During this process, certain amount of energy gets released. This energy is at least equal to the band gap energy of the semiconductor material. The energy, according to Planck's law, is associated with certain frequency. If the energy is more, frequency becomes large. So when recombination happens in a diode, which is made with a semiconductor material having a large band gap energy, there is a possibility for the emission of energy whose frequency is high, falling in light band frequencies. This is the basic principle underlying the functioning of light emitting diodes. The emission may be invisible, like infrared and ultraviolet. It may be visible with any one color. It all depends upon the material, semiconductor material that is used in fabricating the diode. Precisely, it depends upon band gap energy of the semiconductor that is used for fabricating the diode. LEDs have plenty of applications. These applications range from wrist watches to pocket calculators to the transmitters of fiber optic communication systems. Nowadays, they are used even in the design of domestic TV sets. Special diodes, light emitting diodes, Series on semiconductor devices and circuits, lecture number 2.23. LEDs stand for light emitting diodes. They emit light. That's why they are called light emitting diodes. They fall in the category of special diodes. Several applications is with the help of LEDs. One can find LEDs in wristwatches and in several other commonly found applications. With this small introduction, now let us move further to begin the core session. A few points regarding the principle of working of LEDs. Light emitting diodes or LEDs, in short, these are PN junction diodes emitting light. They convert electrical energy into light. The input to LEDs is electrical energy and the output is light. LED action is given by light is given by diodes that are made with direct band gap and high band gap semiconductors. This is the point. The semiconductors that are used for fabricating LEDs, they must have high band gap, larger band gap, and they must be of direct band gap type. Two types of semiconductors are there: direct band gap, indirect band gap. Silicon belongs to indirect band gap material. So you cannot find LED action in silicon diodes. So it must be direct band gap semiconductor and band gap must be large. And LEDs, they work, they function, they emit the light when they are forward biased. When diode is forward biased, electrons and holes are injected into the junction region where they recombine and emit photons, light. The emission is near the junction where recombination is concentrated. So light emission is near the junction. A few points regarding working of LEDs. During recombination, energy emission takes place sometimes in the form of radiation. Energy in the radiation is at least equal to the band gap energy of the semiconductor. According to Planck's law, radiation energy E and its frequency F are related through E equal to HF. In physics, usually it is H nu. Frequency is indicated by nu. But in engineering, frequency is by F. When the band gap is large, radiation frequency also is high. For certain semiconductors, gap energy is so large. This one is so large that the frequency, this frequency, falls in the visible light spectrum, resulting in light emission. So here point is, light means high frequencies. Therefore, for the emission of light, energy must be high. Band gap energy must be high. That's why it is mentioned that LED must use a semiconductor material that has a high band gap energy. Then only the energy gap energy is able to give high frequency radiation, frequency high enough to fall, to make the radiation fall in the light band. This is the symbol, ordinary diode symbol modified by adding two outward arrows, anode terminal, cathode terminal. Here one point is required to be mentioned. LED is operated always under forward biased condition. There is a relation between wavelength of the radiation and band gap energy. This is a standard relation. Wavelength in micrometers of the emission. It is equal to 1.24 by band gap energy in electron volts. In B, functioning is explained. Notice the diode is under forward biased condition. So electrons get injected from right side to left side. Holes get injected from left side to right side. So there is a chance for electrons and holes to meet in sufficient numbers so that maximum amount of recombination is possible. An electron can meet a hole at the end, somewhere here. A hole can meet an electron somewhere here also, but one can easily understand, one can easily notice. In the region surrounding the junction, there exists maximum or good number of electrons and good number of holes. So possibility of recombination is more near the junction region. At the ends, for example, if you consider P side end, far away from the junction region, here holes may be plenty, but electrons are very few, because by the time the electrons cross the junction region and travel towards this end, it may get recombined with some holes. So number of electrons here at the end of P region, here they are small, their concentration is low, so very little recombination. Similarly, N side also, at the end here, terminal end, electrons may be plenty, but holes, their number is very little. So recombination, chance of recombination is very small. This explanation is based on the fact that for recombination to happen, more number of electrons, more number of holes, they must be there available. Then only there is a more chance for recombination. When chance of recombination is more, there is more possibility of emission of light. This is the idea. This explains why LEDs emit light only from the region surrounding the junction. Here small derivation is given for lambda equal to 1.24 by Eg. This is Planck's law, Eg equal to Hf. H is a constant, 6.626 into 10 power minus 34 joules per second. Eg equal to Hf, it can be written as Hc by lambda. C is speed of light. Frequency is speed by wavelength. Therefore, wavelength lambda is Hc by Eg. Substitution and simplification leads us to get lambda in micrometers is equal to 1.24 by Eg in electron volts. Now some more important points regarding LED. Visible spectrum is typically between 380 nanometers and 750 nanometers. Emission to lie in the visible spectrum, band gap energy should lie in between 2.26 to 1.64 electron volts. Silicon is not suitable for LEDs. It is already mentioned, as its band gap energy is only 1.12 electron volts. The minimum band gap energy that is required to emit light is 1.64 electron volts, but silicon's gap energy is 1.12 electron volt. So it is not suitable. Another reason is also there for the unsuitability of silicon. It is indirect band gap material. What is indirect band gap material? Consider energy band diagram of semiconductor. This is valency band, this is conduction band. When electron falls from conduction band to valency band, energy gets released, radiation comes out. The energy that is released is equal to band gap energy, at least band gap energy, minimum band gap energy. Now, in direct band gap materials, the fall is direct from CB to VB. So energy release is equal to band gap energy. At least that much energy gets released. Sometimes it may be even more. Released energy may be even more than band gap energy. In indirect band gap materials, what happens is the fall is not direct. The fall is stepwise. First, from conduction band, it falls to a level in band gap, forbidden band gap, let us say here at this point, to an intermediate level, and energy is released. Naturally, the difference in the energy levels of the particle is small. One can see it is small. Frequency of the energy that is emitted is also very small. When frequency is small, it cannot be, radiation cannot be in the form of light. Now, after falling to an intermediate stage, the particle then falls again down into valence band. In the second fall also, it releases certain energy, but notice here also the energy is small. It is not equal to, it is less than band gap energy. So here also radiation energy is small, so frequency is small, so it cannot be light. So in indirect band gap materials, the released energy, released radiation is of small frequency. Small frequency radiation cannot be light. Another point. So that's why silicon is not suitable. Gallium arsenide is a direct band gap material with band gap energy of 1.42 electron volts. Notice this 1.42 is still smaller than 1.65. Even though gallium arsenide is direct band gap material, its gap is 1.42, smaller than 1.65 minimum required band gap. That's what he is telling. This energy is also not sufficient to emit visible light. Its emission falls in invisible. There are two types of light: visible light, invisible light. So emission from gallium arsenide diode falls in visible part of light, that is in infrared region. This property makes it suitable for use in the design of security systems. Some more points regarding LEDs. LEDs are fabricated with 3-5 semiconductors due to their desirable optical properties. See, this 3-5 refers to periodic table. Direct gap semiconductors are highly conducive for radiative recombination, and because of this reason they are widely used for lead fabrication. However, it is possible to have efficient radiative recombination from indirect gap semiconductors with the help of certain trap levels, and hence they are also used for LED fabrication. So he is mentioning, it is being mentioned here that indirect gap materials are also useful and used to fabricate LEDs. For visible blue light emission, silicon carbide, gallium nitride are used. For other colors, the materials universally used for lead fabrication are gallium phosphide, gallium arsenic phosphide, zinc telluride, and zinc selenide. The materials that are used for fabrication of lead, they are mentioned in this form, tabular form in this slide. If you want a red color emission, then you have to go for gallium phosphide, zinc oxide, this particular combination. Or one can go for gallium arsenide phosphide, aluminum gallium arsenide. If you want orange or red, you have to go for gallium arsenide, phosphide, nitride. Orange is the requirement. Then one can go for aluminum, indium, gallium phosphide. For yellow color, similarly some material. For green color, material. Blue color, these are the materials. Here, the type of material is given. The peak wavelength of the emission is given. Band gap energy is also. Some properties of LEDs, voltage current properties. Voltage and current. Due to higher value of band gap, LEDs typically show a higher forward voltage drop of order of 1.2 to 2.5 volts and often carry current of order of tens of milliamperes. So higher voltages are required to operate LEDs. They also carry higher currents. Optical conversion efficiency. What is this? It is an important figure of merit for LEDs. It is defined as the ratio of optical power output to the electrical power input. So this is a performance index for LEDs. Note the efficiency of radiation increases with the injected current as well as temperature. Efficiency, conversion efficiency, or radiation efficiency increases with the injected current as well as temperature. It depends upon temperature. Applications of LEDs. Visible light emitting diodes find applications in calculators, watches, etc. Infrared emitters are widely used in security systems for optical coupling and safety controls. Gallium arsenide is an infrared emitting LED. We have seen already. Recently, white LEDs are developed and they are expected to replace fluorescent lamps and also incandescent bulbs in near future. White LEDs are made by suitably combining the output from red, green, and blue LEDs to give white light, or using blue or ultraviolet LED output to excite electrons in a phosphor material to high energy levels, which then come down to low energy levels, re-radiating several wavelengths, all combining to give white light. With this, we come to the end of the session on light emitting diodes. Before closing the session, let us recollect the important aspects of LEDs that are discussed in the session. Symbol of LED is given. The principle of functioning of LED. Materials used. Why silicon is not suitable for fabricating LEDs? What materials are required to be used to emit the desired colored light, etc., etc. They are all discussed in the session along with applications of LEDs. Hope this session is useful to you. We meet again soon in another session with a new topic.